Good morning. So let's continue with polar form of CR equations of f of z is equal to u plus iv. So polar form of CR equations are del u by del r is equal to 1 by r, del v by del theta, and del v by del r is equal to minus 1 by r del u by del theta, which are also known as ur is equal to 1 by r v theta and vr is equal to minus 1 by r u theta. So let's see its proof. Since f of z is equal to u plus iv, so take it as equation number 1. Now, as we know that z is equal to x plus iy, it can be written as z is equal to r cos theta plus ir sin theta. And if we take r as common, the z is equal to r cos theta plus I sin theta. And using Euler's theorem, this cos theta plus I sin theta can be written as e to the power I theta. Since by Euler's theorem, e to the power I theta is equal to cos theta plus I sin theta. So we can write z is equal to r e to the power I theta and put the value of z in equation 1. So we have another equation that f of r e to the power I theta is equal to u plus iv, and now take it as equation number 2. Now we differentiate this equation 2 with respect to r and theta. So first, if we differentiate this equation 2 with respect to r, then the right hand side will be del u by del r plus I del v by del r, which can be written as ur plus ivr. And what about left hand side? Left hand side can be differentiated as f dash r e to the power I theta into 1 into e to the power I theta. So our left hand side will be f dash r e to the power I theta into e to the power I theta, and take this equation as equation number 3. Now we differentiate equation 2 with respect to theta this time. So if we differentiate this equation with respect to theta, the right hand side will be del u by del theta plus I del v by del theta, which can be written as u theta plus I v theta. And what about left hand side? Left hand side will be f dash r e to the power I theta into r into differentiation of e to the power I theta, which will be e to the power I theta into I. So this is the differentiation of equation 2 with respect to theta. Now, this equation can be written like ri into under bracket f dash r e to the power I theta into e to the power I theta. And the value of this bracket is equal to left hand side of equation 3. So we can replace this bracket with ur plus ivr. So using equation 3, this equation can be written like Ri into Ur plus Ivr is equal to U theta plus Iv theta. Now, if I open the bracket, this will be minus Rvr plus IRUr is equal to U theta plus Iv theta. Now we equate both the parts, real part as well imaginary part. So if we are equating imaginary parts, we have an equation that RUR is equal to V theta. So we have our first CR equation as UR is equal to 1 by R V theta. Now, if we equate real parts on both the sides, we have the second equation as minus R VR is equal to U theta, or we can say that VR is equal to minus 1 by R U theta. So we have our two equations in polar form, that UR is equal to 1 by R V theta and VR is equal to minus 1 by R U theta, which are known as polar form of CR equations. Next, we will see applications of complex analysis. So our first application is harmonic function, which is also known as potential theory. So let fz is equal to u plus iv, and fz is analytic. Then the real part and imaginary part, both u and v, satisfy Laplace equation. What is Laplace equation? That del square u by del x square plus del square u by del y square is equal to 0, and del square v by del x square plus del square v by del y square is equal to 0. Then u and v are known as harmonic functions. Next application is orthogonal system. If fz is equal to u plus iv, where u and v both are family of curves u is equal to c1 and v is equal to c2. Then these family of curves u is equal to c1 and v is equal to c2 are orthogonal or perpendicular to each other. Next application is flow problem in fluid dynamics. So flow pattern is represented by complex potential function Wz, where Wz is equal to phi plus I psi, where phi and psi both are functions of x and y. Here phi is known as velocity potential and psi is known as streamlines. So this is the application of complex function in flow problem. Next, we will solve some application questions in further lectures. Thank you.